Hello and welcome back to Statistics 1. This is section 9.3, which is the same thing as the previous one. Now we have p-value, which is just a name. There we go. 9.4, huh?
P-value is the z-score?
Yeah. Well, we're getting there. So, Control-C, Control-V from the previous lecture on calculations, and now we're going to take a look at the situation. So let's say that you have 5% significance level, and if you have that, that means that each one of these would be 2.5%, which you can convert using z-score chart. So if you go into the z-score chart, (0.025) is exactly negative 196, which means that the other side would be symmetric 196. Now, you usually memorize these numbers because you just have so many problems that have 5% significance level when it's a two-tail test. So now we are creating do not reject in the middle and reject region if you run into any of these two. And now your p-value is z we get from mu x bar and sigma x bar. And I'll just say data. And then that value is going to fall somewhere in this. So now, let's take a look at a problem. Chapter 9, 9.3. There we go. So problem 966 is asking if z-scores for a two-tail test at 5% significance level get to be rejected or not. So we have 5% significance level, and z-scores are given as 3.08, and another z is given as negative 2.42. This is not LUL, this is level. There we go. Value is at 308, which is here. So definitely reject. And the other one is negative 2.42, which is here, which is also reject. Great. Reject, reject, do not reject. So your rejection region is shaded blue, and as you can see, both of these test statistics ended up in the rejection region. The next problem, 9.67, is asking again for 5% significance level and gives you the z-scores of negative 1.66 and the z-score of 0.52. It's the same picture because it's the same significant. Terrible. Ah. Alright, that's somewhat better. So we have negative 1.96 and 1.96 because that doesn't change, right? At 5%. So that doesn't change. Rejection region. Do not reject and reject. So what do I have? I have negative 166, that's here. And 0.52 would be probably over here somewhere. So do not reject either. So it's either in the rejection region or it's not in the rejection region. Those are the only two choices that you cannot be somewhat in it.
One score that's in the reject and one score that's
Yep,
not in reject.
sure.
And what happens if you get the score that lands on for 1.96?
Do not reject. Good question. Now, can I find, where are the word problems? What is going on over here? Is it a full moon outside or what's going on?
So in words, or you just say the
Well, see, the problem is that, again, no word problems, so they just give you z-scores and you literally compare what's bigger, what's smaller. And it either falls in the rejection region or it doesn't, or it falls into do not reject region. And I finally found the word problems in the 9.4. So I'm not restarting this. I'm just going to say, okay, word problems. Finally. And they are in 9.4 for this. So we can actually do something. Hotels and motels, job gains and losses, work fatigue, teacher salaries, cell phones. What should we look at? Serving time. Any takers? Serving time, of course. According to Bureau of Crime Statistics and Research of Australia, the mean length of imprisonment for motor vehicle theft offenders in Australia is 16.7 months. So we are now in 9.87 problem, 9.4, which are the word problems for 9.2 and 9.3. So we are looking at the mean. So this is your null hypothesis, 16.7 months. Randomly selected motor vehicle theft offenders in Sydney, Australia, had a mean length of imprisonment of 17.8 months. So 100 of these had 17.8 months as a mean. And they also give us that the population standard deviation sigma is 6 months. So at the 5% significance level, do the data provide sufficient evidence to conclude that the mean length of imprisonment for motor vehicle theft offenders in Sydney differs from the national mean? Just differs. So they didn't say less than or greater than, they just said differs, right? So what are we using as the HA? Cannot equal, yes, does not equal 16.7. Good. So that is a two-tail. This is how you know which one to use. Two-tailed. Now, they also gave us a 5% significance level, which means it's the same picture we had so far. So I'm going to use this information to calculate my test statistic, which is going to be that the mu x bar is the same as the mu, which is 16.7, and then we have that the sigma x bar, the standard deviation for our sample mean, is going to be the standard deviation of 6 divided by square root of 100, which is 0.6. So this is what we have to work with. So now your z-score is x bar, which is 17.8 minus 16.7 divided by the standard deviation of 0.6. This is going to be 1.1 divided by 0.6. Oh, you couldn't give me like a little bit more, so it's just 2. Let's see. Give you the answer in 17 decimals over here. 1.83 z-scores, right? They only have the 2 decimals in the chart, so I'm not going to put a lot of decimals there. Now, since we have a 5% significance level, we go and draw the same shape we had so far, and we already memorized our cutoff points because it's the for 5% two-tail. These are the numbers. You don't get to change this, right? If I change, I don't know, 7% significance level or 10% significance or 2% significance level, then these numbers change. But for the 5% two-tail, this is what you have for your rejection regions. Your test statistic worked out to be 1.83. 1.83 is smaller than 1.96, falls in a do not reject. And we have to say as the answer, at 5% significance level, the data does not provide sufficient evidence to reject. Provide sufficient evidence to reject the original mean, right, which we just say H0. It looked good, but it didn't work out. Now, would it work out if we said, does it provide sufficient evidence to show that the mean is actually larger we have to redo the calculation because you don't have the 196 anymore. So what I'm doing now is I'm modifying the problem. So now the problem modified as this. Your alternative hypothesis is that mu is 16.7 months, right? Alternative hypothesis this time around is that the mu is actually larger than 16.7 months using all the same specs. So now I don't have any more, right? I don't have the two sides. I only have right tail at 5% significance level because I'm using greater than. What does that look like as on a picture? And what is the number that it's a cutoff now? So when I draw the distribution, I only have one side. Well, this is generous, or whatever, doesn't matter. So now my 5% is here, and the rest is 95%. And this 5% is the reject, and this is do not reject. I need this number now. Well, I'm going to find that number from the z-score chart when I look at 95%, right, which is converted to area. So now my area is 0.95, and that is going to give me the z-score, which will be the number that we get as a breakpoint. So now when I go into the z-score chart, so when I go to z-score chart, the one that is showing right now has negative numbers. So that's not good one. We need positive numbers. Let me make this larger. No, that's the search. Oh, there, this is the control plus. There we go. So as you can see, you have a little picture on a z-score chart here that shows that all of this stuff is shaded, right? And then you're looking for 0.95. 0.95 is 0.95. Between these two numbers, so 1.645, right? 1.645. 1.645. So when you have area or probability, you're looking for 0.95. 0.9 starts here. 0.90, 0.92, 0.93, 0.95, go back, 7.4. Aha. 0.9495, 0.9505. They are the same amount away from what we need. So we have to take the average of the two z-scores that we get from here. So that's going to be 1.64 and 1.65. When you average them, you get 1.645. So because you're looking for the middle. So this is given by significance level. Significance level of 5% gets you this z-score, which creates the barrier between do not reject and reject regions. Then you use the specs. N is 100, X bar was 18.7, and sigma was 6. You use those specs, right, the parameters, to calculate the test statistic, which will fall into one of the two regions. So mu x bar is equal to mu, which is mu 0, right, which is 16.7. And sigma x bar, this is not changed, is sigma divided by square root of n, which we said was 0.6. So we do have the same z from before, which is 16.7. No, I lied. 18.7 minus, what do I have wrong over here? 16.7 and 17.8. It's 17.8. 17.8. Good. So it's 17.8 minus 16.7 divided by 0.6. We get the same 1.833333 forever. Now you see that that one falls into reject region. See? So it matters which test you use. 1.83. So now, if we look at it this way, we can say at 5% significance level, the data shows sufficient evidence to reject major. So now you're going to go, hold on. We did the same problem, two different ways, and we got two different answers. All right? Well, depends on, first problem was a two-tailed test, and you only got, at 5% significance level, you only get 2.5% from each side. Now, you only do the right tail test, and you have 5% from one side, which means the barrier is moved, and it's actually easier to get and change your null hypothesis in favor of, to reject the null hypothesis in favor of the alternative hypothesis. So now the question is, well, which one is right? Because you can't use, they give you opposite answers, right? The first part said do not reject, this one says reject, right? Well, the answer to that is it depends, right? The way you look at it, which is why, we have to debate certain things. When you have the mean, see, you have your x bar, and your x bar is actually a whole month larger than your national mean that was established. So, in my never humble opinion, the second one makes more sense because you can see, you took a large sample of 100 prisoners, right? I mean, this is Australia, everyone is, right, prisoner. I mean, descendant of a prisoner. What you have is a large sample of 100, and they are showing that the mean should be higher, which is what I used in my hypothesis. I said higher. I wasn't just going, no, you're wrong, right? Because that's what the previous case was. Did not say, look for higher, look for lower. It just said, no, you're wrong. That's it. And in that case, right, we didn't get to reject it because there was not sufficient evidence to show to reject. But in this case, when you are pointing out that the actual mean that you found is larger, and you are saying that this is too small, right? It's too low in comparison to what you found through your research with 100 people, your claim passed. Your claim passed because you were more specific of what you are looking for, right? And just being more specific, the entire 5% was here. So 2.5% cutoff point is there, and the 5% cutoff point is here. So as you can see, right, this test statistic gets to be on either side, right, depending on what you're claiming. So if you have a good data, large data, solid data, right, you can make these claims with larger than or smaller than, and in that case, it's a little bit easier to get rejection. When you just do not equal to, well, immediately you have a two-tailed test, so whatever your significance level is, and significance level is basically the confidence. Significance level on this side, confidence level on this side, so it's the same thing. So when you have the significance level of 5%, right, it gets divided into two. So if you are specific, you get to use the entire thing. If you are not specific, then you get to use half on each side. And that's the goal. So finally, lessons 9.2, 9.3, and 9.4, it's all the same thing, all the same calculation, except the first two are explaining the concept and give you those baby steps of figuring out the cutoff point in the 9.2, then figuring out the test statistic P in 9.3, and then in 9.4, bringing them together into a word problem. So it's technically all one lesson, which is what just happened. It was not planned, but it worked out that way. Now, what is the bad thing about 9.2 and 3? 9.2, 3, and 4? The title had sigma is known. So we get to use the z-score, right? What's 9.5? It's sigma is unknown, so you just get to replace sigma with t-score and then just use the sample for more realistic results. So in 9.5, you are using, instead of z-score chart, you're using a t-score chart. Calculation is the same, just like we saw in chapter 8 when we went from z-score to t-score between 8.2 and 8.3. Now, between what we did so far in chapter 9 and 9.5, you will be using a t-score chart to obtain the test statistic, because you are no longer going to have your sigma. You will have S, which is what you can get from the sample. So we still have X bar, that's good, and now instead of having sigma, we're going to have S. And the whole thing is identical, other than are you looking in the Z chart or you're looking in a T chart, right? And we know that the T chart is a little bit trickier to use because it has a degree of freedom and all of that extra stuff. And 9.5 is where the course ends. That's the last section where you end. So, well, look at that. We do have 6 minutes, but let's use those 6 minutes to talk about the test. So I'm just going to write here. We didn't get the chance to, but look into it if you're taking stats too. I mean, come on. Right, 9.5 sub Z's for T's, and then do the same problem. So you are using the t-score chart, and this is actually what we are always going for, because you always have all of the properties, all of the things for the sample. You have the sample mean, which is X bar. You have a sample standard deviation S, and that leads you to use the t-score chart. And then the significance level is still in the z-score, and it's still the same numbers. So 5% one way is 1.645. Two-tail test So that doesn't change. Let me just write all of these. I mean, you should be able to obtain them, but then if you are not understanding, then you are memorizing, right? So left tail test, negative 1.645. Now these are only for 5%. Obviously, if the percent changes, then they're different. Again, 5% on the right tail test for the mu larger. So this is mu less than mu 0. This is mu larger than mu 0 on AJ. And this is mu different than mu 0 with a 2.5% on each side. And the numbers were negative 1.96 and 1.96. So if you are having a problem with 5% significance level, doesn't matter 9.4 or 9.5, this is the setup. And then you go and you calculate your test statistic, which falls in the reject region or do not reject region. What happened? Yeah, pass region, right? So you are rejecting your original mean, right, the established mean, in favor of the hypothesis mean. Great. Good. Your next exam, which is on Monday, is on chapters 6, 7, 8, right? And it has the good old reading, calculating z's, looking at the z-score chart to get area, figuring out area and probability looking at the z-score, t-score chart, which is what we covered last time, with the degree of freedom. So the question, like one of the favorite questions, right? Let's say you test your IQ and your IQ comes out to be 117. What is the percentage of people that have lower IQ than you? What is the percentage of people that have higher IQ than you? So when you have that kind of a question, right, you know that the middle is the 100 IQ, so that your IQ is then, or 116, is just above, right, because standard deviation was taken to be 15. There are some books that say, some papers that say 16 as well. So you are just above. So your z-score must be 1.0 something, right? Because the z-score is calculated as x minus mu divided by sigma. So that's your 116 minus 100 divided by 15 to calculate your z-score. Once you have your z-score, you can then go to the chart and see area to the left, right? That's going to be percentage of people with a lower IQ, and then the area to the right is the amount of people with a higher IQ than you, right? So now you can do this with body weight, you can do this with shoe sizes, you can do this with, you know, whatever else, pretty much anything that is normally distributed. And then also featured on the exam, the sample means, where mu is equal to mu x bar, which is mean or means. And then the formula, which we already seen 3 times or 4 times today, for standard deviation of sample means, which was population standard deviation divided by the square root of n, which is the sample that you looked at. Also the knowledge that the higher the sample, right, the more observations you have within a sample, the better, the data is better, right? And you can do better statistics with a larger sample, we saw that whatever it was, 7-1 or 6-1, whatever it was, the one that was those never-ending charts of right. We saw that if the sample size is larger, the means were better predicting the population mean. The normal distribution, right? Why we do these samples and means? So even if the distribution that you're looking at is not normal, the mean of means, right? The distribution of all sample means normalizes data if your sample size is larger than 31. And we had that picture also shown. So those are just ideas. So some of these are kind of theoretical. Your calculations mainly pertain to Z and T-score calculations, talking about area to the left, area between two, area on the outside of two, like we did over here for a two-tail test. So you can have a question to calculate area to the left, area to the right, area in between, area on the ends, right? So all of those skills are important in different situations. And then at the end, connect those areas to probabilities so that you can claim that probability of, right, so-and-so chance to, right? Your quiz 2 is due tonight. Quiz 3 opens tomorrow 6 a.m. Quiz 1 will open, what's better, Saturday or Sunday? Sunday?
Could you just make it open for
It's bad. That,
just for quiz 1, to have it open on any day?
how about Friday to Sunday?
Yeah.
All right. Fine. You win halfway. All right, guys. I'll see you Monday at 4.